name is Alexey, welcome to the session, and yes, I will be talking on artificial intelligence and how it applies to PDF world. Just a few words about the company I represent. Duolab is a service provider company with roughly 50 engineers. We're experts in PDF, and Duolab is a lead very PDF developer, but we also specialize in graphic arts and science-intensive solutions, but not afraid of new technologies and apply them day to day as well. And we build dedicated teams for long-term collaboration. The outline of my talk today is pretty straightforward. First, we'll take a look at the recent achievements in AI, and then we'll peek into how deep artificial neural networks actually make it work. We'll discuss in which areas PDF can benefit from AI, and we'll see how to build AI pipelines for PDF to achieve your goals. And of course, we'll cover a bit on the problems that still remain unsolved. So in 2016, AlphaGo, an artificial intelligence system developed by DeepMind, managed to beat the world's greatest Go player of the past decade in an astonishing 4-1 match. And during the course of the game, the AlphaGo managed to beat a series of highly inventive moves, which were not known to the community of Go players yet. And to clarify, this is not just about the computational power, because the total number of board configurations that are possible in the game of Go is much more bigger than the total number of atoms in the universe. And in fact, if you take all the atoms in the universe and you replace each atom with a copy of the universe, only then would the total number of atoms in this system would be comparable to the possible number of board configurations in the game of Go. Waymo, an Alphabet company, has been driving its cars in Arizona since October 2017 without a safety driver or any human at all behind the wheel. And a group of researchers in Stanford designed an AI algorithm for detecting signs of disease in chest x-rays for humans last year, and in just over a month of development, their algorithm outperformed expert radiologists in detecting pneumonia. So we see that artificial intelligence is already here. It's finding new drugs, it's discovering new drugs even, it's finding your friends on photos, it's recommending you places to go out, and it's searching your search results by relevance and scanning for fraudulent transactions. So what seemed impossible 10 or 20 years ago is now an astonishing reality. So what about the electronic documents? There is some research in it, and there are even dedicated conferences on this subject, and one of the most prominent of them is International Conference on Document Analysis and Recognition, and some of the research is based purely on PDF. And we see the trend that there is emerging research on deep learning approaches, which are actually state-of-the-art in artificial intelligence and machine learning. But of course there are some drawbacks. Those researches are typically based on moderate-sized data sets, and they typically focus on smaller subset of problems like detecting single tables or like subset of objects. And of course there are interesting projects related to AI and documents, and one of them is a project that can convert mock-up images to HTML and CSS code that actually looks like the mock-up. And I believe some of the PDF vendors already use AI in their systems. What's really important is that AI is able to deal extremely well with unstructured data. So unstructured data is everything from images to audio to text, and classical algorithms have been struggling very much with unstructured data. We developed some heuristics, but now we develop AI algorithms, and they deal extremely well with unstructured data. And PDF, which is a composite format, is also an unstructured data format. The percentage of unstructured data today is estimated by different sources to be up to 80%, and this number has risen by 15% over the last 5 years. So I attributed PDF to be an unstructured data format, but you might argue that we have tech PDF, we have document structure, we can make PDF structured actually. But of course, tagged PDF is still not default for most PDF producers. 3+ trillion PDF files are already out there, and most of them are untagged. We have to deal with them. Among the PDF-A family, only level A requires text structure, but it doesn't impose any condition on how good the text structure is. And even the documents that are tagged are sometimes of very poor quality. The transition to tagged PDF, which is a trend now, but it will take some time. And of course, AI is applicable even for tagged PDF and PDF UA. We'll see about that in the rest of the talk. So this is just an example. On the left, you can see a table with different number of cells in rows, and what's most important is that there are no call spans there. And this is a document that is valid according to the specification, but it's really hard to deal with this document. And this document is generated by one of the major PDF producers nowadays. And on the right, you can see an example of a PDFA level A compatible document and its text structure, but it literally doesn't give you any information. And of course, we have a ton of untagged PDFs. One of the prominent groups are scientific papers. They have pretty complex layouts, and almost none of those publications are tagged, and they are extremely hard to tag, actually. So the tasks that are solved by artificial intelligence are very different, but it turns out that the algorithms that are used are quite similar, and they are called deep artificial neural networks. They are state-of-the-art nowadays, but they were invented back in 1940s and only became widely used in the latest 10 years. And what enabled us to use them are increase in computational power, and especially GPUs, graphic cards, and increasingly large amounts of data. So let's take a closer look at how those artificial neural networks actually work. So on a very high level, the neural networks accept raw data, which might be of different formats like image pixels or audio signal, but it might be something more classical like numbers. And neural networks, which might be of different types, produce a result which can actually be of the same type that the raw data, or different type, of course. So neural networks are able to produce images, they're able to generate audio and text. When it comes to neural network architecture, neural networks consist of several layers, and each layer consists of several neurons. So neurons are marked with circles in this slide, and there are connections between neurons that are marked with arrows. The first layer is typically an input layer, and the last layer in the neural network is typically an output layer. Neurons accept activations from neurons in the previous layers, and they compute activations on their own. So the way this activation is computed is by taking activations from neurons from the previous layers, or if it's an input layer, then the activations are actually the inputs to the neural network, and then the weighted sum of products of inputs and weights is computed, and weights are the parameters associated with a neuron. And then a nonlinearity function is applied, which a mathematical concept which allows a neural network to compute much more complex functions. So there are many types of neural networks, as I said, but one of the most studied one and one of the most applied one is the deep convolutional neural networks, and they actually enable you to deal with images. They're applied for image classification tasks, for object detection in images, so they are able to output a B-box with an object placed in an image, and they are even able to do segmentation tasks, so they can provide fine-grained pixel coordinates of an object in an image. And convolutional neural networks also consist of neurons, but neurons in each layer are grouped into something that's called feature maps or channels, and they can be thought of as a mapping of original image into something that looks like a grid. So in case of images, it can also be treated as image, of course. So two foundation operations in deep convolutional neural networks are convolution operations and subsampling or pooling. Convolution operation takes as input a matrix and produces another matrix as a result. And the parameter of this convolution operation is the filter. And the way the result is computed is by applying filter to all the possible positions in the source matrix and taking the sum of the products of the corresponding numbers. So in this case, we see that filter has non-zero numbers in the lower left corner and the upper right corner, and this means we have to add 28 and 1 in this case, we get 29. Then we move the filter to the next position and we compute the next number, and so on. So this is the convolutional operation. And actually, convolutions are not something new. They are used in image processing already nowadays, and you might all have used them implicitly while editing images in your favorite image editor application. So let me just show you two examples of convolution. So images are, of course, matrices of pixels, so we can think of them as matrices of numbers. And if we think about grayscale images, just for simplicity, and if we consider those two particular convolution operations, particular filters, the horizontal one takes the top row and subtracts the bottom row, and of course it's all summed. And the same for vertical edge detector, but it does this for columns. So it takes the numbers in the first columns, it subtracts the numbers from the last column, and everything is added up. And those filters actually allow us to detect horizontal and vertical edges, as obvious as it may be. And if we take a look at the example here, so on the left you can see the original picture is grayscale, and if we apply a horizontal edge detector, which means the convolution with the filter from the previous slide, the output would look something like this. So remember that for images, black pixels are low numbers, small numbers, and white pixels are large numbers. So we may think of it as the convolutional operation giving us high activations for horizontal edges. So you can see on the right image that we don't see those vertical stripes, we only see horizontal ones. And if we apply a vertical edge detector, it's just the opposite case. We don't see any horizontal lines, we only see the vertical ones. And if an image doesn't have any horizontal lines, if it only has vertical lines, the result associated with horizontal lines detector will just be empty. So we've taken a look at the convolutional operation. The other one is pooling, and pooling is also pretty straightforward. It's even simpler than convolution. So the way it works is by dividing the original source matrix into submatrix regions, hopefully of equal sizes, and then mapping each subregion to a single number. And the way the mapping works, it can take either average of those numbers or maximum. So it basically allows us to reduce dimensionality of our matrix. So some of the parameters of the neural networks are just embedded into its architecture. For instance, the number of times we will apply convolutions and poolings, or the size of the filter. In this case, I've only demonstrated 3x3 filters, but of course you might use 7x7 or anything up to 15x15, say. But some of the parameters, like the numbers in the filter, are something that's trained during the training stage by the neural network itself. And the way the neural network is trained is by taking the outputs from the last layer, and remember that last layer typically produces the outputs of our neural network, and then we have to come up with a loss function that, given the original, the true answers, and the answers produced by our neural network, it will compute the distance or the similarity, the same thing, of those outputs. And then it becomes a loss optimization problem with respect to weights, and this is a purely mathematical thing that is solved with gradient descent. What's important here is that typical neural networks that solve real problems nowadays might have hundreds of layers in them, and each layer might have several hundreds actually of feature maps, and each feature map is associated with a filter which might be everything from 3x3 to say 11x11 or even more. So it's not uncommon nowadays for neural networks to have several millions of parameters, and what it means is that we need a lot of computational power to train it, and we need large data sets to train it as well. So the trend here is that the bigger the network, the more data you need to train it, but the better accuracy you get as a result. So convolutional neural networks are something that's
a bit easier to understand. So because we're dealing with images, we can take a look at single neuron and see for which input images it's activated most. So remember that each neuron outputs an activation as its result. And because at layer 1 neurons only observe a small portion of the image, and this portion is defined by the size of the filter in the convolution operation. It only observes a large portion of the image and detects small features, but those features can be like edges or different directions of edges, or it might detect solid patches or even green solid patches specifically. If we move to layer 2, we can see that each neuron is associated and can implicitly look at a larger portion of the image because of the combination of convolutional and subsampling operations, so it's already able to detect more complicated patterns. And if we go all the way to level 5, let's say, which is pretty early just yet, but the neurons are already able to recognize images of dogs, of different breeds, of course, just yet, and it's able to recognize like wheels and birds and stuff. So those are different neurons and different image samples for which the neurons are largely activated. That was just a convolutional neural network example, and there are many types of neural networks. They solve different problems. For instance, if you want to do natural language processing or speech recognition, convolutional neural networks are not what you should apply. There are different types of neural networks for that, mostly recurrent ones, and they are able to keep track of the content, of the context, excuse me, actually. And when we solve a specific problem, we should think actually what's going on inside our brains. So if we want to recognize structure in a PDF page, let's say, when we take a look at a PDF page, what's going on inside our brains? Do we remember the contents of the last page? Do we pay attention to labels on that page that say like table? It's probably a combination, and neural networks also allow you to use those combinations. So modular neural networks allow us to combine several neural networks and use them and apply them to the task we're solving. Of course, the trend here is that even for similar tasks, different neural networks, different architectures might perform quite differently. And we used to define heuristics in classical algorithms before, but now we have to apply our heuristics and our imagination to neural network architectures design. Why do the neural networks work so well? Actually, we don't know, in the sense that we don't have strong mathematical proof compared to classical machine learning algorithms, for which we actually have theorems that give us upper bounds on the error rate given the sufficient data set. But what we know is that artificial neural networks can approximate any function on the training set, and we know that they work extremely well on the real-world problems. And of course, this is not a cryptography after all. We usually tend to apply artificial intelligence to tasks that are handled by humans nowadays, for which we don't have deterministic solid algorithms, so maybe having some error rate is not a big issue here. So what about the applications to the PDF world? The most obvious one that probably comes to mind of everyone here is structure recognition for intact PDF. And once we've recognized headings, tables, and paragraphs and all the other structure elements on a page, and once we've determined reading order, which is of course quite difficult, we can use a screen reader tool to provide accessibility of such PDFs. But of course, there are many cases where it's not obvious even for humans. Like in this case, is it a two-column layout or is it just a table? We probably don't know. The other applications, repurposing, which is something that we're already, as a PDF community, looking into. Reflow after adding or removing content. And after you're able to reflow your document after adding or removing content, you can do amazing things like immediate translation of a PDF document is just an example. Of course, it's also important not only for us humans, but also for machines themselves. If the document is accessible, it's much easier to index it in the search system and provide you better search results. Another application, PDF UA. PDF UA is probably associated in our community as something that's quite expensive and where a lot of human effort is required. And the key requirement of PDF-A specification is that content shall be marked in the structure tree with semantically appropriate tags in a logical reading order. And this is where a lot of human effort is put into. So we have Matterhorn protocol checkpoints, which have 136 checkpoints, and 47 out of them are marked as manual. So this is an obvious place for improvement. Even if it requires a new version of the specification, this is something we can and should improve. So let's take a look at some of examples from Matterhorn protocol. The first one, list is not at least, but no value for the list number and attribute is present. So this probably doesn't seem like rocket science to detect odd at least nowadays, right? So this is probably something that we can do. If we take a look at this third one, for instance, content is tagged as a table for information that is not organized in rows and columns. Well, maybe that's a bit trickier, but maybe still manageable. If we take a look at the last two ones, the structure type and attributes of a structure element are not semantically appropriate for the structured element, or tags are not in logical reading order. So those are just two checkpoints, but they actually mean a lot, and they are very hard to satisfy even for humans. If we take a look at this example, is it a table? For me, it looks like a table, but it turns out that in the original document, it was author actually attributed this to a figure. So sometimes the clear intent of the semantics in the document is only known to the author, and we as consumers of that document cannot know it. Of course, there are many more applications. We can categorize incoming documents like invoices and improve our workflow and eliminate human from that workflow. In GDPR era, redaction is a very loud topic, and there is a very interesting concept in data science and the neural network world. It's called generative adversarial networks, and if we apply them to the redaction problem, it would be a very interesting thing. It would be like two neural networks that would compete one against the other. So the first one would try to remove sensitive information from the PDF document, and the second one would try to guess whether all the traces of the sensitive content were removed or not. And when I say traces of the sensitive content, it doesn't necessarily mean the visual traces, because there might be some non-visual traces that are specific to PDF content stream instructions, for instance, that are not obvious for humans how to reconstruct, but might be obvious for an artificial neural network. We can generate alternative text for images, and image captioning is something that neural networks are already very good at, and there are competitions where the artificial neural networks actually outperformed humans at image captioning. We can repair broken documents and reconstruct to Unicode, for instance, or something else. We can do OCR, but it's already there, actually. And we can even do some peculiar things that you might not think of when you think about artificial intelligence. We can convert between formats and do compression and optimization. Let's take a look at how real-world class problems in related to artificial intelligence and data science are solved today. Many companies have their data science departments, and they hire dedicated people to deal with those problems. But there are also alternatives to that. There are different websites hosting data science competitions. One of the most prominent of them is called Kaggle. And the competitions there are real. They are offered by big companies and even by governments, and the prizes there can be up to up to several $1 million, actually. One of the examples is an airport screening challenge offered by one of the USA governments, I believe. So the goal was to detect forbidden items in the airport screening data. So what I mentioned earlier is that neural networks might be extremely hard to train, and you need a lot of data to actually train it, and a lot of computational power. But there is a concept which is called transfer learning, and it helps to mitigate this problem. Transfer learning is a very powerful concept which allows you to take an artificial intelligence algorithm, a model, which solves a different problem but in the same area, and you can, in sense, reuse that knowledge and apply it to your problem. For instance, if you want to detect forbidden items in airport screening images, let's say, you can reuse a model that just classifies images into, say, 80 different categories, and there are models out there, there are competitions that provide such models. So even though those forbidden items that you're looking at, like knives and guns, might not be among those 80 categories, because at earlier stages neural networks actually detect patterns that can be reused for different applications, and we saw them before, so they can detect small edges like circles and something like this. So you can already reuse that information and apply it to your problem. Of course, you would need to adapt the model, change some layers in your neural network in the later stage so that it outputs what you want it to. But by transfer learning, you need less time in training it, you need less computational power, and actually you need less data set size. So you just fine-tune the already existing model into your problem. So this is an extremely powerful concept. But of course there are competitions among big companies where they typically don't reuse anything. So there are different competitions on speech recognition or natural language processing and image recognition, object detection and so on. But of course those companies spend weeks and even months in training such models, and they have access to large clusters for training. Andrew Karpathy, a very prominent AI researcher and director of AI at Tesla currently, published an interesting blog post where he claims that classical stack of programs are explicit instructions to the computer written by a programmer, and today we have new software which are programs that are written in neural network weights, and programmers just define constraints in the behavior. So he claims that large portions of problems share the property that it's easier to collect data rather than to try to come up with an algorithm with all those heuristics to actually deal with a problem. And software 2.0, of course, is not to replace classical programs. It will just take over some areas. And in the future we'll have, and even now actually, we have a challenge of choosing between a 90% accurate model that we understand, that is deterministic, versus a 99% accurate model we don't understand. So as a PDF community, we provide, as vendors, we provide a lot of tools for build PDF tools in classical software, but we don't provide anything to build software 2.0. And as data science community is very open, it drives it forward and it allows a very rapid progress. And transfer learning is a very powerful concept, as I mentioned. By transfer learning, when you are building a self-driving cars, all the cars actually interchange the experience. You don't have, well, while you're a human, you have a limited experience in driving during your lifetime, but those cars share the experience from all of them, and it's something like 3,000 years or even more. So by being more open, the progress is much more rapid. So we should think about it. But of course we have to start from something. Let's take a look at the outline. How can we build a pipeline for PDF to solve a PDF-related problem like structure recognition? So to train a deep neural network, you need to come up with a neural network architecture. And as I mentioned, this is an area where there is no silver bullet. You have to be inventive and you have to play around. So I will skip it. We have to come up with features and training set and loss function. Those are required concepts. So in terms of which features to extract, it's pretty obvious that we can use a rendered representation of a PDF, which actually gives, in a very few bits of information, it gives us a lot of information about the document. But we are losing something, so we can also extract glyphs and B-boxes from the content streams and lines and so on, or we can use a combination of them. Sometimes, because it's a PDF and it's a specific format, we'll need to deal with its structure. Like when dealing with links, we would want to extract the link from the destination. Sometimes it makes sense to use of the, it makes sense to use semantics if it's present. For instance, if there is a label on a page saying that containing a table word, for instance, it probably means that somewhere on the top of that label or on the bottom of that label there is a table. There is also a promising approach of end-to-end machine learning, which in this case would be just taking all the sequence of raw content stream instructions and trying to make the neural network to predict what we want it to. And actually, by this, it would learn what are those peculiar content stream instructions really mean. But although a very promising approach, it's infeasible nowadays because it requires enormous amounts of data. Ground truth database. This is something you should probably start with after you've decided on your features. Which sources can you use? Tagged PDF is an obvious one, but as I said, a lot of tagged PDF is improperly tagged or poorly tagged, so you might want to evaluate its quality before actually using it. You can use structured documents and convert them to PDF. That's another approach. You can use manual markup, so you can take untagged PDF and hire some people to manually mark up it for you. You can use semi-automatic markup by using heuristics in deterministic and deterministic algorithms to mark it up for you and then correct it manually if needed. To get those files, you can crawl web pages or you can use and download existing document corpora. Of course, you always have an option to generate those documents yourselves. A very interesting concept used mostly in data science competitions, not in production environments, are data augmentation. So by playing around with your data, by skewing, cropping, rotating your images, you actually get a few samples for free. And it actually improves the performance of neural networks. Calculating loss function. This is also something that's very specific to a problem you're solving, and you have to apply your imagination. But if you're dealing with simple objects, if you're predicting simple objects, for instance, if you want to get bounding box of a table in a page, so you get a bounding box, the rectangle, as a result, and you can use a loss function like intersection over union, which actually computes what it's called. It computes by how much two rectangles, predicted one and the correct one, are intersected. But if you're dealing with more complex tasks, you will probably be dealing with tree-like structure, and this means that you will want to normalize it first to reduce the nesting and probably use a tag subset, because PDF specification is maybe too rich for artificial intelligence to train at the moment. When you want to actually implement the loss function, you might either write your own custom tree comparison algorithm, or you can, for instance, represent trees as strings and use existing string comparison algorithms, and there are quite a few of them, and they work actually quite well. So the ground truth database actually provides us more than just the source to train our neural networks. It can serve to the community as well. If we're thinking about PDF UA validation, for instance, this ground truth database can be an expert opinion system to reach consensus on some files that we often argue about. When you participate in it, you get a vote and you can express your opinion. And it also can serve as a quality measurement system for different implementations. So it might be an interesting marketing advantage for your artificial intelligence system to claim that you are 99.5% accurate on the PDF association dataset, for instance. If we're talking about the ground truth database, we're talking about large amounts of data. So you might want to divide responsibility to store those large amounts of files and maybe introduce a penalty for file unavailability even. Such a system might be very open, or it might be closer, like invitation only. And actually this seems like an interesting use case for blockchain, because you probably don't want to centralize all those things, and all those items in the list are implemented in different blockchain projects already. So I think it's quite feasible if there is an interest in it. Of course, with huge benefits from AI come great challenges. If you take a look at those two images, they look identical to us actually. But the problem is that the first one is recognized by Google Image Classifier correctly, whereas Google Image Classifier sees a dog on the second image. So what the heck, you might ask? The thing is that researchers took an image of the dog and they gradually transform it to the target image, still maintaining the dog classification. And what's really fascinating is that they worked with the system as a black box. They didn't know the implementation, they didn't know how the neural network, how Google algorithms work. And they tricked it into believing that there is a dog somehow in this image. And those are called adversarial examples, and this is a hot area of research nowadays in AI community. Sometimes there is no single answer. As I mentioned, only authors sometimes can clearly know what the intent of, what the semantics of the document is. And this is an infamous example for PDF UA community. In a newspaper, you don't have a clear reading order. There are other challenges. PDF specification is very rich, and I only mentioned a small subset of it. PDF specification also consists JavaScript, 3D annotations, and other stuff that is actually designed for interacting with humans. And of course, artificial intelligence will find it very hard to understand it. And this is probably not, these are not the areas that we should apply it to. Another challenge. We have to decide somehow where lies this point of when we are actually ready to accept AI and replace us with it. It's probably obvious that 100% accuracy is inachievable, so we should find what we will compare it to. So we can just take a random sample of people group and ask them to perform the task that our neural network is performing and measure and compare the performance. But maybe sometimes it's not enough. Sometimes you need domain area specialists actually to do the task and to compare the performance of the neural network too. And wisdom of the crowds works here as well. So if you take a group of people, you will tend to get higher accuracy than from just a single person. So voting applies here. And what's really fascinating is that voting applies to machine learning algorithms, to AI algorithms as well. So if you have a set of AI algorithms, independent ones, each of which is, let's say, 95% accurate, so a sufficiently large group of such algorithms can perform, say, 99%. That's not uncommon. So to summarize, AI is going to be everywhere, including the PDF world, and it is going to be better than humans in many areas, and it will replace us in many areas. But sufficient dataset is a vital component to start building the AI system, so this is a short-term goal for us. And we, as a PDF association, we should provide tools for building software 2.0. It makes sense to do it because it will attract more attention to the community and it will allow us to solve our problems faster as well. PDF UA is one of the areas that I believe is going to be largely affected by artificial intelligence. And with the new version of specification, that might be the case, automatic validation is going to become a reality actually. Of course, it's quite hard to be very open in a challenging and competitive environment, but we should try to do it because the benefits that we get by it are much larger. Thank you.